Hi everyone. Today we'll talk about the idea of elimination as a factorization of a matrix. Whenever we talk in math and we say the word factorization, it means representing this matrix A as a product of two matrices L and U. The reason for using the letters L and U in our case will be L standing for a lower triangular matrix and U staying for the U referring to an upper triangular matrix. Why is this possible? Well, no matter whether A is invertible or not, last time we talked about invertibility, this time we have absolutely no restrictions on A. So let me start there by saying that A can be, well, I should say A is an arbitrary M by N matrix. So what I'm trying to say here is that all matrices have an L times U factorization. A could be invertible, it could not, or doesn't have to be invertible, obviously, because it doesn't even have to be a square matrix. So where is the idea of factorization coming from? Well, remember, when we talked about elimination, we started with a matrix A. We applied a bunch of elimination steps, say E1, then E2, then so on, EK, for example, and we arrived at a matrix U. If I were to write this as a product, it goes like this. So we start with A, then we apply E1 first, so that's the first elimination step, for example, and we apply it to the left on A. Then we apply the elimination step E2, and so on all the way to EK. And this allows us to reach at the upper triangular matrix U. Now remember, we talked about this. All of these eliminations matrices are in fact invertible, which means that we can multiply this equation on both sides by the inverses of the matrices. So if I want the inverse of a product, that is a product of inverses, but written in the opposite order. Why is that? Well, let me just take one step where I first multiply both sides by EK inverse. So only the last matrix. What happens is that this part over here, EK inverse EK, is just the identity matrix. And so on the left side, I'm left with EK minus 1, then E2, E1A, and on the right-hand side, I have EK inverse U. And if I continue in this manner, what I will get is that A equals E1 inverse, E2 inverse, all the way to EK inverse times U. Now, recall that when we eliminate under the diagonal, so all of these E's are elimination matrices that eliminate under the diagonal, which means they're all lower triangular. So each of these matrices is lower triangular. That means that their product is also lower triangular. So it turns out that the product of these elimination matrices is the matrix L that we are looking for. So since we can always eliminate to an upper triangular matrix, it may have a row of zeros, nothing wrong with that, but these E's, they're always invertible. So this matrix L is always going to be invertible, meaning that it is a matrix of passage between A and U. Now, when we look at the product A equals L times U, L is the matrix that takes us from U to A. So L takes us from U to A. Because remember, matrix multiplication means that when we multiply by a matrix, we actually act by that matrix. L acts on the rows of U to take us back to A. And this will be our strategy for finding A. We could certainly try to find it by looking for these E matrices over here, E1, E2, E3, EK. But there is, in fact, an easier way to do it, and I will show you that way on an example. Okay, let's look at this matrix 8, 4 by 4 Pascal matrix. Why is it Pascal? Because if you notice here, there is a pattern. Imagine there are zeros here. Then you would have sort of 1 plus 0 is 1, 1 plus 0 is 1. Then here you have 1 plus 1 is 2, but then 1 plus 0 over here, 1. So you have a nice structure. 3 plus 3 is 6, 3 plus 1 is 4, 3 plus 1 is 4, and so on. Anyway, this matrix is interesting because it has a very nice LU shape, a very symmetric one. Obviously, the matrix is also symmetric. If you look at what is under the diagonal is the same with what is above the diagonal. But anyway, let's try and find our LU decomposition. So we start with the pivot. It is again elimination that takes us to the LU decomposition. So standard things. We're not going to look for matrices E that only eliminate one entry, but rather we'll do it how we've done it before. We'll eliminate everything under that first pivot. So we have R2 minus R1 into R2. That will eliminate in the second row. R3 minus R1 into R3 will eliminate in the third row. And R4 minus R1 into R4 will eliminate into the second row. What we get is the first row is the same, 1, 1, 1, 1. Now the second row is 0, 1, 2, 3. The third row is 0, 2, 5, 9. And the last one is 0, 3, 9, and 19. Now the next step is to identify the second pivot and eliminate underneath. Now we will have two operations, and those will be R3 minus 2R2 into R3, R4 minus 3R2 into R4. The result, so the first two rows stay the same. I'm just going to copy them. 1, 2, 3. And now we have 0, 0. Then 5 minus 4, that's 1. 9 minus 6, that's a 3. Then we have 0, 0. 9 minus 6, that's a 3. 19 minus 9, that's a 10. We're almost done. Now we have the last pivot and we need to eliminate with it. The operation there is R4 minus 3R3 into R4. I'm going to go a little bit down. I'm going to need this space. All right. And now the answer is 1, 1, 1, 1, 0, 1, 2, 3, 0, 1, 1, 3, and we have 0, 0, 0, and then 10 minus 9 is a 1. I think I copied something wrong here. This should be a 0. Okay, and this is our U. Now, how to find L? What we have here with these operations at each step is taking us from A to U. But remember, we are trying to go back from U to A. So let's change that direction going this way from U to A. What we can do is reverse the operations at each step. So this operation can be reversed by changing the minus into a plus. I'm going to write those inverse operations in green. So here we are going to have R4 plus 3R3 into R4. This is the inverse operation. Remember that. So maybe I should write it here. Inverse operation. Now, if you pay attention to these operations, what is interesting is that to R4, we are adding R3. So changes are done gradually in a way that don't affect anything else. Okay, let's continue and write all inverse operations at each step. So the previous step, we can, I guess what I was commenting previously is more interesting here. The inverse operations are R3 plus 2R2 into R3 and R4 plus 3R2 into R4. And what I'm trying to say here is that both of these are getting changed with R2, which means that the two operations are independent of each other. We are adding R2 to R3, we're adding R2 to R4, so it's not like we have an intermediate change in between. These are kind of independent operations. And I guess I should add an arrow in the opposite direction for the green ones. So the green operations act in the opposite way. All right, R2 plus R1 into R2 is the first operation. R3 plus R1 into R3 and R4 plus R1 into R4. So these are the operations. Now, how can we find the matrix L? Well, to find L, apply the inverse operations to the identity matrix. Let's see if I can squeeze all of them in so we don't change boards. So now I'm going to start with the identity matrix. It has ones along the diagonal and zeros everywhere else. And my first operation is going to be R4 plus 3R3 into R4. Remember, we're going backwards. So what does this do? It adds a 3 in the fourth row. Remember, our new matrix needs to be lower triangular, so it makes sense. We're going to have these ones here, zeros above, and then a 3 is added in the fourth row right here. Then the next set of operations are R3 plus 2R2 into R3, R4 plus 3R2 into R4. So we have changes in R3 and R4. The first two rows stay as they are. And then in the third row, I will have a 2 here and the 1 there. And in the last one, I will have a 3 here, 3 there, and the 1. Zeros everywhere else. And the last three operations are R2 plus R1 into R2, R3 plus R1 into R3, R4 plus R1 into R4. And what we get is, notice how when we were adding, so the first place where we changed was right here below the third pivot, because the last elimination step eliminated below the pivot. Then the next two pieces were added underneath the second pivot because the corresponding elimination steps eliminated under the pivot. And finally, we can expect all the changes to be seen here because the original operations, the forward operations, were meant to eliminate there. Now we are recovering what we have eliminated. So I know that all my changes are just in the first column because I'm changing with R1, and R1 has a 1 in the first column and zeros everywhere else. So I know I'm just getting 1, 1, 1, 1, 1, 2, 3, 1, 3, 1. And this will always be the case when you're writing the matrix. So this is the matrix L. When you're writing the matrix L, you will first see changes here, then you will see changes there, and then you will see changes there. So in fact, you could just go and write those coefficients. The coefficient 3, 2, 3, and then here really we have 1, 1, 1, and they just enter the matrix L. So we could simply write what L is. But when in doubt, just apply the operations if you can't see them right away. Otherwise, you should know where the location of that 3 is just by realizing where it eliminated. Then the location of these 2 and 3, where they need to go. Then where these ones need to go that multiply R1. All right, we'll talk more in the next video.